The simple action of breathing in and out has inspired scientists to create a new technique for generating clean electricity. Engineers have designed a device that transforms water into fuel, based on the way our lungs work. 100 times thinner than a human hair, the gadget splits water into oxygen and hydrogen, which can be used to create carbon emission-free energy. This method could help existing green energy technologies, including fuel cells, to run more efficiently, researchers say. These are currently used to power hydrogen buses and cars, and could be used to power whole cities in the future. Stanford University set out to develop better electrocatalysts, materials that increase the rate of a chemical reaction at an electrode, an electrical conductor used in batteries and other energy storage systems. Experts look to the lungs for inspiration, in the belief that the breathing apparatus used by mammals is one of the most sophisticated systems for two-way gas exchange found in nature. With each breath, air moves through the tiny, passage-like bronchioles of the lungs until it reaches small sacs called alveoli. From there, the gas must pass into the bloodstream without spreading out, which would cause harmful bubbles to form. It's the unique structure of the alveoli, including a micron-thick membrane that repels water molecules on the inside while attracting them on the outer surface, that prevents those bubbles from forming and makes the gas exchange highly efficient. It is this intricate system that the team based their clean energy system around. Clean energy technologies have demonstrated the capability of fast gas reactant delivery to the reaction interface, but the reverse pathway, efficient gas product evolution from the catalyst-electrolyte interface remains challenging, said Professor Junior Lee, the first author of the study. The first part of the process, similar to exhalation, produces hydrogen by passing voltage through water molecules at the electrode of the battery device. The oxygen and hydrogen produced are transported through a thin membrane, similar to the alveoli of the lungs. Conventional devices use carbon for this membrane, but the team used an ultra-thin polyethylene membrane, which results in a more efficient reaction. The second stage of the process is more like inhalation and generates energy through a reaction that consumes oxygen. Oxygen gas is delivered to a catalyst at the electrode's surface, creating energy as the molecules pass through conductive metals on the inside of the device. To achieve their aim, the Stanford team made a membrane using plastic film with tiny pores on one side which repel water. Similar to the way alveoli work, the membrane repels water molecules on the inside while attracting them on the outer surface. They then sealed the edges to make a small pouch with a metal layer on the inside. They coated the repelling side with gold and platinum nanoparticles that speed up the chemical reaction. When they applied a voltage to the water to split it, the hydrogen and oxygen gases are transported through the very thin alveolus-like membrane. The lung-inspired design is still in the early phases of development, and has some room for improvement before it will be ready for commercial use. Since the ultra-thin membrane is made of plastic, it cannot tolerate temperatures higher than 100 degrees Celsius. This could limit its applications, said Professor Lee. The team believe this material may be replaced with similarly thin non-porous hydrophobic membranes capable of withstanding greater heat. The full findings of the study were published in the journal Joule.